Hello, my name is Max Wasserman, and today I'll be discussing my recent TMLR paper, Stabilizing the Kumaraswamy Distribution, which I carried out with my advisor, Gonzalo Mateos, at the University of Rochester. This work focuses on the Kumaraswamy distribution, an expressive beta-like distribution well suited for latent variable modeling, due to its tractability advantages and closed-form reparameterization. We identify critical numerical instabilities in its relevant distribution functions that we believe have hindered its adoption and propose a stable reparameterization grounded in modern scientific computing techniques. This fix unlocks the Kumaraswamy for scalable use in probabilistic models. We showcase its utility in several settings, including contextual multi-arm bandits, where we propose a new method, the variational bandit encoder. Here's a quick overview of today's talk. We'll begin with a brief review of latent variable models, a fundamental approach within probabilistic machine learning. Next, we'll narrow our focus to latent variable models with bounded interval-supported latents, and introduce the Kumaraswamy distribution as an attractive option for this setting. Then, we'll shift to contextual multi-arm bandits, where I will review the current dominant approaches and introduce our proposed method, the variational bandit encoder, and conclude with a look at promising directions for future work. We begin with probabilistic models, where a model defines a family of distributions over data, and learning means finding parameters that best explain the observations. In fully observed models, like logistic regression or naive Bayes, all variables are observed. These models permit tractable maximum likelihood estimation of the parameters, as we can directly evaluate and optimize the likelihood. Latent variable models, abbreviated as LVMs, extend this by introducing unobserved or latent variables and represent a powerful modeling approach which enables rich likelihood construction, prior knowledge incorporation, and efficient sampling, but also introduces challenges, namely inference, or computing the posterior distribution over latent variables, is often very challenging, and maximum likelihood-based learning is often intractable. Latent variable models define a generative process by introducing unobserved latent variables. We specify a prior over the latent variables and a likelihood that relates the latent variables to observed data. Their product gives the joint distribution, and to assess model fit, we marginalize over the latents to obtain a marginal likelihood. The evidence, or the log marginal likelihood, is the quantity we seek to maximize in maximum likelihood estimation, but its gradient is often intractable, posing a significant obstacle to training LVMs. Since the evidence gradient is generally intractable, we turn to variational inference, where we introduce a variational distribution Q with parameters phi to approximate the true posterior. This provides a tractable lower bound on the evidence, also called the elbow, which we aim to maximize. Maximizing the elbow with respect to the model parameters theta aims to improve model fit, corresponding to parameter estimation. Maximizing the elbow with respect to the variational parameters phi encourages Q to match the true posterior by minimizing Kell divergence, corresponding to approximate inference. Optimizing the elbow requires computing gradients with respect to both theta and phi, but the elbow involves an expectation under Q, and Q is parameterized by phi, complicating the elbow's gradient with respect to phi. Estimating gradients of expectations with this form can be challenging, and we quickly review a few common approaches. If we naively apply Leibniz's rule to bring the gradient inside the integral, we lose the expectation form because the gradient of Q is not a valid probability distribution. This blocks us from using standard Monte Carlo estimators. There are two dominant approaches to recover Monte Carlo estimators of the gradient. First is the score function estimator, also known as reinforce, which rewrites the gradient using the log derivative trick. It works quite generally, but the variance is often too high for efficient use in elbow optimization. Second is the reparameterization trick. If we can express samples from our distribution Q as a deterministic function of our distribution parameters and fixed noise, then we can move the gradient inside the expectation while preserving the Monte Carlo structure, enabling low variance estimates of the gradient and efficient elbow optimization. In practice, this is the preferred approach in modern deep variational inference. With the necessary latent variable model machinery in place, we can turn our focus to an important class of latent variable models, those with latents supported on bounded intervals. We'll also introduce the Kumaraswamy distribution, an expressive, reparameterizable distribution well suited for this setting. Many real-world applications can be well modeled by latent variable models involving latent variables constrained to bounded intervals. These include continuous control settings, conversion probabilities in ad ranking, mean reward estimation in bandits, and event occurrence probabilities in forecasting. This motivates the need for an expressive, reparameterizable latent distribution with bounded support. When selecting a variational distribution for latents on bounded intervals, we want 4 key properties. Support on the unit interval to match the posterior's domain. Note that the support on the unit interval can be trivially scaled and shifted to any bounded interval. We want expressivity to capture complex posterior shapes. We desire support for the reparameterization trick for low variance gradient estimation. And finally, we want simple distribution functions for fast and stable evaluation. Let's look at 3 candidate distributions. First, the tan-H squashed Gaussian, which is reparameterizable but limited in shape. For example, it cannot represent the uniform distribution. Second, the beta distribution, which is expressive but lacks the reparameterization trick. Finally, the Kumaraswamy distribution, denoted as KS, can take the same prototypical shapes as the beta, including the uniform distribution, and supports the reparameterization trick. The Kumaraswamy distribution is often viewed as a beta-like distribution with tractability advantages. Both the Kumaraswamy and the beta distributions are defined on the open unit interval and are parameterized by 2 positive shape parameters, A and B. The Kumaraswamy's PDF closely mirrors that of the beta, but without the beta function normalization, making it simpler to compute. What sets the Kumaraswamy apart is its closed-form inverse CDF, enabling the reparameterization trick in variational inference. Now, I'm not the first to point out that the Kumaraswamy is well suited for variational inference. Here's a GitHub request from Jasmine Bastings, a researcher at DeepMind, advocating for the inclusion of a stable Kumaraswamy. She says, Kumaraswamy variables are simpler to reparameterize, which is not the case for beta variables, whose techniques are complex and typically lead to higher variance. We would like to use it in our research, probably so would others. Leading researchers across a wide variety of domains, including natural language processing, modern large language models, interpretability in neural networks, and Bayesian optimization, have publicly asked for a stable Kumaraswamy. And the struggle for a stable Kumaraswamy implementation spans years. Ongoing developer threads spanning back to 2018 reveal how machine learning library maintainers have struggled to implement a stable Kumaraswamy distribution, consistently hitting issues like NANs and invalid reparameterized samples. Even today, pulling the latest main branch of PyTorch or TensorFlow surfaces the same issues. Right? The Kumaraswamy still remains unstable. Let's take a closer look at the numerical issues using PyTorch's provided Kumaraswamy implementation. On the left, we plot the PDFs of several desirable Kumaraswamy distributions. The jagged, spiky curves reveal instability in the evaluation of the density. In the center, we plot the inverse CDFs used for reparameterized sampling. These too exhibit jaggedness, and past a certain point, they collapse to 0 due to underflow. Here, 39% of inputs from the uniform distribution map to exactly 0. On the right, we see the result of the problems in the inverse CDF. The reparameterized samples form visibly quantized histograms, and 39% of the samples collapse to 0. So while the Kumaraswamy is appealing in theory, these numerical instabilities severely limit its use in practice. While inspecting the Kumaraswamy's expressions, I uncovered the hidden numerical culprit, catastrophic cancellation, which is a loss of precision when subtracting nearly equal numbers. This occurs in the term log of 1 minus the exponential of x, which becomes unstable as x approaches 0. Machler in 2012 proposed a stable alternative using widely available numerically stable primitives. The plot on the right shows the difference. The naive version in red quickly goes unstable, while Machler's version in blue maintains low error across the domain. The presence of this unstable term in the Kumaraswamy isn't obvious from its standard parameterization, but it occurs in all relevant distribution functions, namely the PDF and inverse CDF, as well as their gradients. To address the instabilities in the Kumaraswamy, we introduced two contributions. First, we reparameterize the log PDF, inverse CDF, and their gradients using unconstrained parameters log A and log B, and isolate every instance of the unstable log of 1 minus the exponential of x, shown here in red. Second, with these unstable red terms isolated, we can now directly substitute in Machler's numerically stable formulation, ensuring accurate evaluation. We can now use these expressions to implement a new Kumaraswamy distribution in PyTorch and revisit the problematic distributions from before. In the bottom row, we see that all major issues have been resolved. The PDFs are smooth and well behaved. The inverse CDFs no longer underflow, and the sample histograms now accurately reflect the continuous shape of the target distribution. No quantization artifacts and no point mass at 0. In short, it restores the behavior modelers reasonably assume from a well-defined distribution. To validate our stabilized Kumaraswamy, we evaluate it across a diverse set of latent variable modeling tasks. Shown here are just two examples from the paper. First, contextual multi-arm bandits, where it shows better exploration-exploitation trade-offs with lower regret. And second, GNN-based link prediction on standard datasets, where it improves uncertainty quantification and calibration. Shortly after posting this work to arXiv, we were excited to hear positive feedback from the community. One standout example came from the unexpected area of vector quantization for search. Data stacks leverage the unique properties of the Kumaraswamy to learn non-uniform quantization strategies, achieving a 15% improvement in compression, reducing the size of vector embeddings, and yielding significant storage savings in large-scale vector search systems. Dr. Mariano Tepper, their vector search R&D lead, reached out directly, and we discussed follow-up collaboration since. And finally, we have a pull request pending to integrate the stable Kumaraswamy implementation into PyTorch's main branch. Let's now turn to contextual multi-arm bandits. Bandit problems are a natural fit for latent variable modeling, and particularly for bounded interval latents like probabilities. This will set the stage for introducing our final contribution, a novel contextual bandit model called a variational bandit encoder. Multi-arm bandits model sequential decision-making, where we attempt to learn from feedback tied to our actions. The term multi-armed bandit comes from a classic casino analogy. You face several rigged slot machines, each with a fixed but unknown payout rate. In order to maximize winnings with a limited number of pulls, you must balance exploration, trying machines to learn their payouts, and exploitation, sticking with the ones that seem best so far. At each step, you must choose one of K arms and receive stochastic feedback in the form of a binary reward drawn from a Bernoulli distribution, parameterized by a fixed but unknown mean reward mu with value between 0 and 1. Now, if you knew the arm with the highest mean reward, denoted mu star, the optimal arm selection strategy or policy would be to play it every time. But since mu star is unknown, the challenge is to learn which arms are best while still collecting high reward. The standard objective is to minimize regret. In other words, the expected difference between the reward of the optimal policy and that of your own, which measures how far your policy falls short of the best fixed decision in hindsight. A natural extension of the basic bandit model is the contextual bandit, where each arm k also comes with an associated n-dimensional feature vector denoted xk, which may carry information about the expected reward. For instance, imagine each slot machine has visible features, maybe its color, manufacturer, or year of production, which could contain correlations with mean rewards across arms. The challenge is to learn a policy, meaning a rule that maps context and action reward history to a strategy for choosing arms, which balances exploration and exploitation to minimize regret. This is a vast and mature field, but I'll briefly highlight two broad families of approaches: the point estimator approaches and the Bayesian parameter modeling approaches. Point estimator approaches posit a parametric function E with parameters theta, often a linear or neural function, that maps context vectors x to mean rewards mu. The parameters theta are estimated from observed data, typically through maximum likelihood and updated periodically. Arm selection is based on predicted rewards, optionally adjusted from using a fixed exploration heuristic. Common examples of such methods include greedy methods, epsilon greedy methods, and upper confidence bound methods. Advantages of point estimator methods include the low complexity. Fitting maximum likelihood models tends to be quite straightforward, and this makes these methods accessible to many practitioners. The methods are also interpretable. As the models directly output predicted mean rewards, arm selection decisions are transparent. The disadvantages include the often poor sample efficiency and the difficulty in incorporating known information about specific arms into the model parameter estimates. The limitations of the point estimator approaches help motivate Bayesian approaches. The setup remains the same as in the typical contextual bandit case, but now we introduce a latent variable model in which the context and rewards are observed random variables. By performing inference, we obtain a posterior distribution over the unknown mean rewards, visualized here in the last row. We derive a policy from this posterior distribution to balance exploration and exploitation. A common policy is Thompson sampling, which selects the arm with the highest sampled mean reward from the posterior. The traditional Bayesian approach extends this point estimator method by treating the parameters theta of the reward function as latent random variables. In this approach, the posterior belief over the mean reward, which guides the policy, is not modeled directly. Instead, the mean reward is a derived quantity, and its posterior is induced by the posterior over model parameters. There are two primary strategies for performing inference in this setting: Monte Carlo sampling methods like Langevin dynamics or Gibbs sampling, which aim for asymptotically exact posterior samples, or variational methods such as Gaussian or dropout-based approximations, which trade accuracy for efficiency by approximating the posterior with a simpler tractable distribution. These methods present certain advantages. For example, they provide a principled, data-driven way to quantify uncertainty over mean rewards, enabling exploration through Thompson sampling. But they also come with distinct disadvantages. For example, Monte Carlo sampling can be prohibitively expensive, particularly for expressive models such as neural networks, due to the need to store the full dataset in memory and perform often hundreds of likelihood and gradient evaluations for each posterior sample. They can also pose scaling issues. For example, online variational methods often involve operations quadratic in context vector dimension, limiting users to small context sizes. Both approaches can also be sensitive to the specification of hyperparameters, often requiring expensive tuning, for example, step sizes, burn-in, or stable matrix version. Finally, they also have a limited ability to incorporate prior information on arms, as priors are placed on reward function parameters theta, not on mean rewards. We're looking for an approach that combines the strengths of both paradigms. From point estimator methods, we desire low complexity and scalability. Particularly, we want to ensure compatibility with modern, high-dimensional applications requiring linear scaling with respect to context dimension, dataset size, and parameter count. We also desire interpretability. We should be able to inspect model outputs and understand its beliefs about specific arms. From the Bayesian parameter modeling, we want principled data-informed handling of mean reward uncertainty to guide exploration and exploitation trade-offs. And ideally, we want something neither approach provides, a way to directly incorporate prior knowledge on mean rewards. The high-level idea of our proposed approach is to use a neural network to output an approximate posterior over mean rewards. To build this, we need to answer two questions. What should the probabilistic model be? In other words, what are the variables we want to model and how are they related? And how do we train this neural network so its output approximates the true posterior under this model? We now introduce our proposed approach, the variational bandit encoder, which we feel combines the attractive strengths of both point estimator and traditional Bayesian approaches, while allowing direct incorporation of prior knowledge over specific bandit arms. The key idea in the variational bandit encoder is to introduce a latent random variable mu that explicitly models the unknown mean rewards, enabling a prior to be placed directly over these values. In the variational bandit encoder, we define a conditional prior over mean reward variable mu given the context x. This can be hand specified, for example, specifying the parameters of a beta distribution, or learned, for example, using a neural network to encode some parametric distribution or even a normalizing flow. We also define a reward likelihood conditioned on the mean reward variable mu. Here, we use Bernoulli rewards, with mean rewards supported on the unit interval, but the framework readily supports alternatives, such as Gaussian likelihoods for linear reward models. Both the conditional prior and reward likelihood shape the posterior distribution over the unknown mean rewards mu. With the model defined, we can now introduce a variational posterior Q to approximate the true posterior over mean rewards. This approximation is parameterized by a neural network encoder E with parameters phi. Given context vector x, the encoder outputs the parameters of some variational distribution Q, which is trained to match the true posterior. Since we focus on the binary reward setting, each mu k is supported on the unit interval, and so we can set the variational posterior to a fully factorized Kumaraswamy distribution, as it effectively balances expressiveness and tractability. But more expressive options, for example normalizing flows, are also compatible with this approach. With the model and variational posterior defined, we can now turn to the training objective, the elbow, composed of a data fidelity term and a prior matching term. Since the variational posterior Q supports the reparameterization trick, we can efficiently optimize the elbow, which in practice amounts to stochastic gradient descent, typically requiring just a single forward and backward pass with a neural network. All components involved in this process are standard in modern auto-differentiation libraries like PyTorch. The key modeling decision is the form of the conditional prior. The choice can be informed by the data regime. When there is abundant data, we can learn a flexible prior, for example, using a neural network, which takes the context vectors as input, allowing the model to interpolate prior beliefs across the feature space. Or we can set the prior to the uniform distribution for an exploration-promoting regularization effect. With limited data and strong prior knowledge, we can manually set priors. For example, hand-specified beta distributions based on this prior knowledge. Here's how we can use the variational banded encoder for Thompson sampling at each round. Denoted in red, we first pass each context vector through the neural network encoder to produce the Kumaraswamy parameters, defining the variational posterior over mean rewards. We then perform arm selection through Thompson sampling, denoted in blue, by drawing one sample per arm from its variational posterior and selecting the arm with the highest sampled value. In gray, we indicate the pulling of the selected arm, the observation of the Bernoulli reward, and the recording of the context action reward triple into the replay buffer. Finally, in green, we construct the elbow from the updated buffer and take a gradient step to update both the model and variational parameters. To evaluate the variational banded encoder, we use a standard synthetic contextual banded task with 10,000 arms and 2,000 rounds. We compare three variants using different variational posteriors, the Kumaraswamy, the beta, and the tan-H squash Gaussian, under an exploration promoting uniform conditional prior. All achieve low regret, and the Kumaraswamy variational posterior achieves the lowest. We compare against Langevin Monte Carlo with Thompson sampling, a state-of-the-art contextual banded approach, denoted here as LMC-TS, which is performant but incurs high sampling costs. We find that the variational banded encoders are far more efficient, and the Kumaraswamy variant even outperforms the Langevin Monte Carlo baseline in regret. Let's quickly summarize these three contextual banded approaches. Point estimator methods, whose graphical model is shown here on the left, such as greedy, epsilon greedy, and upper confidence bound methods, assume a fully observed model where both contexts and rewards are known. A function with parameters theta, learned through maximum likelihood and periodically updated, maps each context to an estimated mean reward, optionally adjusted using a fixed exploration heuristic like epsilon randomness or confidence bonuses. These methods are simple, computationally efficient, and yield transparent decisions, but they can be sample inefficient and struggle to encode prior knowledge about specific arms. On the right, we show the canonical graphical models for the two latent variable modeling approaches, the parameter modeling approach and the variational banded encoder. The parameter modeling approach treats the reward function's parameters, theta, as latent random variables. The core challenge is performing posterior inference over theta, typically using sampling or variational methods. While this enables a principled uncertainty-aware exploration, it often introduces substantial complexity and limits scalability, especially as context dimension, dataset size, and model capacity grows. Additionally, because theta often defines a black box function, such as a neural network, incorporating prior knowledge about the specific arms is difficult in practice. In contrast, the variational banded encoder models the mean rewards mu directly as latent variables. This allows for the introduction of a conditional prior over mu, making it straightforward to inject domain knowledge about specific arms. The model structure is compatible with modern, deep variational methods, supporting simple, scalable neural network solutions, which are often critical for modern systems. We'll now wrap up by showing how the variational banded encoder can be used in the common setting of movie recommendations. Further, we'll show that the variational banded encoder's ability to incorporate prior beliefs directly over mean rewards can be used to address cold start problems. Consider the movie recommendation setting. The feedback matrix has rows representing users, with each user containing a context vector that may include demographic features like age, gender, viewing history, and preferred genres. Columns represent movies, with each movie containing a context vector that may include metadata such as genre, average IMDb rating, release year, and semantic embeddings of the movie description, for example, from a pre-trained text embedding model. Each user-movie pair defines an arm, with its context vector formed by concatenating the respective user and movie context vectors. In the data-rich regime, where we have plenty of interaction data, we have two attractive options for the conditional prior. We can set the conditional prior to the uniform distribution for an exploration promoting regularization effect, or we can learn the conditional prior, for example, using a neural network to map from the user-movie context to encode some parametric prior distribution. From the variational posterior, we can use another neural network to map from the user-movie context to encode a Kumaraswamy distribution. After maximizing the elbow, shown above, we can directly inspect the model beliefs on each user-movie pair by visualizing the variational posterior. In other words, pushing the concatenated context vector through the variational posterior encoder neural network and visualizing the Kumaraswamy distribution its output defines. Note that the variational posterior tends to place low posterior probability over, for example, older men liking the child's movie Frozen, but high posterior probability over, for example, the hit classic Rocky. In system cold start settings, we have no user item interaction data. The feedback matrix is empty, and the reward likely to determine the elbow vanishes. Here's one way we could proceed. We select a representative subset of items, for example, the movies Rocky, Frozen, and Grease, and assign prior distributions based on believed demographic preferences. For instance, for the movie Rocky, we may specify a distribution, a beta distribution, with significant prior probability mass over high mean rewards for older men, reflecting our prior belief that this demographic will find this movie appealing. Whereas for older women, we may assign a beta distribution with prior probability mass shifted downward, reflecting our reduced confidence in this movie's appeal to this demographic. In this setting, maximizing the elbow simply minimizes the KL divergence between the variational posterior and these manually specified priors. After doing so, we expect the network to interpolate our prior beliefs across feature space, yielding meaningful estimates of reward probabilities in regions with no hand-specified priors. This enables a principled warm start across the entire system, allowing the model to make informed recommendations before any interaction data has been collected. The setting of item cold start can be treated similarly, where if we have strong prior beliefs that certain demographics will enjoy or not enjoy this new movie, here Casablanca on the right, we can encode that as a manually specified prior. Maximizing the elbow and visualizing the posterior model beliefs again shows how our prior beliefs can propagate to inform the posterior. We can address user cold start similarly by assigning prior distributions to a subset of movies based on believed preferences for the new user's demographic. And again, maximizing the elbow and visualizing the posterior model beliefs shows how our prior beliefs can propagate to inform the posterior. Finally, we address promising direction for future work. The variational banded encoder was introduced as only one part of the Stabilizing the Kumaraswamy TMLR paper, but it warrants deeper evaluation, particularly on real-world datasets. It is especially well suited for settings with high dimensional ARM features, significant prior knowledge on expected rewards, and sparse interaction data. To enable broader adoption, especially in critical applications, it's important to establish theoretical guarantees, such as asymptotic optimality and regret bounds. If you have questions, feedback, or a multi-arm banded application where you think the variational banded encoder would be a great fit, I'd love to hear from you, and feel free to reach out. Thanks.